Did that? I just like, 'cause I saw you out there, and then I saw it's gone. I thought.
Oh, one of those.
Yeah, maybe they keep going every time. Okay, good morning, everyone. Good morning. I don't normally get a response. Thank you. That's so nice. Welcome. Sorry. Yes, we should. Yeah, I deserve more respect. You're absolutely right. Welcome to the Climate and Energy College. My name is Nick Parry. I'm one of the PhD students here. Today we have a very special guest in Dr. Ben Henley, who's going to be talking about water supply risks at 1.5 and 2 degrees of global warming. Before we proceed, I would like to acknowledge the traditional owners of the land, the Wurundjeri people of the Kulin Nation, pay my respects to their elders past, present and emerging. So Ben is splitting his time currently between the University of Melbourne and Monash University. He's just run from a meeting between the Earth Science teams from both those universities. So we thank you for squeezing us in. He's an associate investigator at the ARC Centre of Excellence for Climate Extremes. He lectures at Monash University in paleoclimatology and future climates. He's done work in both academia and industry, consulting on water issues. Should be a very, very interesting and relevant seminar. So without further ado, welcome to Ben.
Thank you very much, Nick, and thank you all for coming. I really appreciate your interest in this work, and so I guess we're in the middle of a drastic situation in Australia with the current drought, and that's really the context for this talk. But we're thinking today a bit more about the future, the 1.5 degree world that we're heading very rapidly towards, and the 2 degree world, which is looking ever more likely. So this is the current drought, the last 24 months of rainfall deficiencies that we see. And the darkest red here is the lowest on record rainfall that we've seen in the instrumental record for approximately the last 120 years or so. So you see very large areas of New South Wales and Queensland and other parts of the country that are in severe drought right now. If we move that forward 1 month, so this is very most recent data for the last 24 months, that drought is spreading. We have experienced an unprecedented event with regards to winter rainfall for, if you just look at New South Wales and ACT, the last 3 years, at no point in the instrumental record have we seen 3 years of failed winter rainfall. And this is probably one of the most important reasons behind the agricultural impacts of the current drought. At the same time, and this is probably more the focus of my talk, is urban supply systems are actually at quite low levels. 40s, 50s, and 60s, 63.8 for Melbourne, that was yesterday, or quite recently. And some of these other storages are at very low levels that are getting into the zone that caused so much of the problem with the Millennium Drought. At the same time, we've of course had absolutely catastrophic bushfires so far, and it's only just been the start of summer, of course. 6 people killed, more than 600 homes, a huge area of land bush burnt, and many people on the ground are saying unprecedented conditions with regards to catastrophic bushfire in parts of New South Wales and other parts of the country. And of course, just thinking back to the 2009 bushfires, where we had absolutely catastrophic loss of life, 180 people killed, of course, temperatures well into the 40s, thousands of homes destroyed, and also very large areas burnt. Again, that at that stage was unprecedented conditions. And just to start to think about the drivers of bushfire risk, and it's probably no surprise, but things like fuel load, but dryness. What is driving bushfire risk in the long term over very large areas? I kind of make a case for drought being a significant impact on that. Certainly temperatures and humidity and wind speed changes are a big impact too. And remembering that the catastrophic bushfire rating came from as a result of the 2009 bushfires. And just thinking back though, what was the sort of precedent of the 2009 bushfires? The Millennium Drought. This is the rainfall decile map for the Millennium Drought, roughly 97 to 2009, just before we had the heavy rainfalls in 2010 and 11, which sort of in some eyes ended the drought. This was the conditions, and look at where the most severe impacts of those bushfires occurred, right in drought ravaged Victoria. So some of the impacts here, of course, of the Millennium Drought were very, very significant. Many billions of dollars of agricultural losses, $10 billion of desal plants built around the country, and below median rainfall for more than 10 years in many places. Extremely severe drought. It's a concern. It's a really serious concern for our cities, for the security of our water supply. We have a whole number of challenges when it comes to supplying water to our cities. First of all, we know we've got really high variability naturally. Quite without climate change and without population growth or anything else, the variability in the Australian landscape is massive. We've got these influences from the surrounding oceans that are affecting rainfall year to year, and there's a lot of persistence in that rainfall behaviour. We've seen changing rainfall patterns. The seasonality of rainfall appears to be changing, particularly in the south. I'll touch on that in a minute. And at the same time, we've got a rapidly urbanising population, people moving into cities, and those cities are growing rapidly. We have short observed records, so we don't really understand the natural variability in the system beyond the last century. And during that century, of course, particularly the latter part of that, we've seen change to the climate system, which complicates the factors around understanding the natural variability. So we're really vulnerable to these long droughts. We've basically built huge cities with massive reservoir systems that are somewhat vulnerable to these droughts, and we're finding that we need to find a climate-independent source of water, i.e. desal, to help with that, along with all of the other measures that we can do to back up our water supply systems. And on top of all of that, we have quite a lot of uncertainty about exactly how climate change will play out. So this is the situation, this is the scenario that we're dealt with. I'll touch on a few issues before I get into the 1.5 and 2 degree work. Just wanted to point to, these are scatter plots of monthly rainfall and inflow. So rainfall on the x-axis for each of the seasons, and y-axis is the inflow into the total inflow into Melbourne's main 4 storages. This is the water that we drink. Rainfall here, inflow there. In the color, I've represented the temperature. And so what I'm showing here is, first of all, there's a lot of seasonality in rainfall. We know that we get most of our rainfall in the cooler seasons. We also get most of our runoff in winter, and particularly spring as well. It's a really important time. if you look at for a given rainfall, you'll notice that in some of the seasons we have what's called energy limited situation, and other seasons we have a water limited situation. So essentially evaporation is driven either by a lack water limits or energy limits. And the point here being that you get higher evaporation in summer. And so with what we project and what we have observed is somewhat consistent with this, a change in the seasonality of rainfall from winter-dominated, cool season-dominated rainfall to warm season, and we may see some slight increases in rainfall in summer and likely decreases in the cool season. That rainfall falling on a dry, hot catchment is going to lead to lower runoff. And so this may be very well behind some of the rapid decreases in inflow that we've seen for not that significant a reduction in rainfall. On top of that, and associated with that, we've seen that in the drought, so I'm plotting here, this is work by Margarita Saft and Murray Peel and others, colleagues of mine, who have looked at the rainfall runoff relationships in specific catchments around the country. And they've noticed that for some catchments, the rainfall relationship change has actually shifted. The rainfall runoff relationship has actually shifted to essentially produce less runoff for a given amount of rainfall. And that during the drought, this behavior changed. For some catchments after the drought, it returned to pre-drought conditions. For other catchments, it's remained the same. So some of the challenges about better understanding that is a focus of future work. I thought I'd also just touch on that concept of long-term variability and better understanding the natural variability in the climate system, as well as understanding climate change. And so we've got some work to better understand that variability using paleoclimate reconstructions from regions, from records around Australia. And you can, I guess, ask the question, how would you operate this system differently if you had this much more data to plug into your models and to better characterize that natural variability? So that's part of the impetus behind that work. It's called a VicTrip project that we're working on. And just a little snapshot of the work coming out of that project. We've gathered in the paleoclimate records from all of the corals and tree rings and ice cores and speleothems from the Australasian region. And we're now building reconstructions for Melbourne's main inflows and also for major storages, irrigation storages. And so what you see here is the total inflow into Melbourne's main storages, or what would have occurred if they were there for the last 4 centuries. And you can see the decline in inflows relative to this long-term variability. You can see a few quite severe droughts popping up in the past, but also quite a bit of uncertainty around this because we lack proxies that are actually in the region. So we have to do analysis on the basis of proxies that exist. As part of that, we're looking at developing new records for better understanding the long-term variability, basically using fancy scanning methods that can look at very high resolution, 25 micron resolution of wood properties. And these wood properties, particularly at high altitude, have been linked to various aspects of hydroclimate. So it's quite exciting to think that we may actually be able to somewhat accurately reconstruct inflows or rainfall or snow depth for several centuries into the past by digging right down into the wood properties of these really long-lived these species. That's quite an exciting piece of work that we're working on. So keep an eye out for that. But in the absence of that information, we've done an analysis looking at the risks at 1.5 and 2 degrees, those Paris levels. And I guess the impetus for this work is, of course, the Paris Agreement, which we're all hoping will come into action. And we're currently watching COP25 and watching what's happening over there. But the Paris Agreement aims to pursue this 1.5 limit, but something that is not that well understood yet is what are the real impacts for a place like Melbourne in terms of if we reach 1.5, does that mean our water supply is secure, but it's not secure at 2 degrees? So some of these questions are still unresolved, and that's the motivation for this work. There's been some recent work using metrics like the PDSI, this Palmer Drought Severity Index. It's an index basically for drought, and it's mostly associated with agriculture. There's been some work on that using the CMIP5 ensemble and climate model ensembles, and also single model runs at stabilized at 1.5 and 2 degrees. But our work uses a time slice method developed by Andrew King and others, which really allows for the use of the full CMIP5 ensemble and to looking at the global warming levels of 1.5 and 2 degrees and what the local impacts at those levels would be. So this is a method that Andrew developed and has been used quite a bit now. On top of that, we have a whole series of hydrological approaches that we can kind of team up with the climate modeling approaches to better model and understand the local variability of catchments, for example. So putting all this together, we are essentially aiming to answer this question. Can we say, or can we determine whether water supply risks are sensitive to those quite near-term warming levels, really? And so we need a nice method to evaluate that risk. And that's what I'll talk about now. So just starting at the global scale, this is a figure of the median precipitation change at 2 degrees in a 2-degree world, according to the global climate models that Andrew and others published in this paper. And where we've shown colour, that's where 2/3 of the models agree on the sign. And what you immediately see, and particularly where we're focusing on these 3 large regions that are well observed, so we can evaluate the models in these regions. Quite consistent drying at a time where we have 2 degrees of global warming in these 3 regions. So if you look then specifically inside those boxes, we now have Southwest North America, the Mediterranean, and Southern Australia shown here. And on the x-axis of each of these figures, we have the change in precipitation compared to 1961 to 90 levels, and the change in temperature. And not surprisingly, as we go from a natural being the dark purple, the current world, so natural was essentially modeled using the so-called HIST-NAT simulations of the CMIP5 ensemble. Current period being a decade around about the current time. And then future worlds, 1.5 and 2 degree world, using the whole suite of these RCPs, if you're familiar with that terminology, at the 1.5 and 2 degree levels globally. So what are the local changes inside those boxes in terms of precip and temperature for these global change points? And what we see is that in these 3 regions, we get at the same time warming, we get quite coherent and consistent drying using these simulations. This is a concern. Warming and drying doesn't equal more inflow. I'll just briefly show some observations for some important catchments in Victoria that we're looking at. So first of all, the Eildon catchment, Lake Eildon being a really important irrigation dam in Victoria, and these 4 main water catchments, that's the water that's coming out of all of our taps, essentially coming from there, with obviously some contribution from desalination and other sources. But this is the last 70 years of inflows into Melbourne and Eildon. There's a pretty clear and consistent decline since the 50s in the inflows, which is I guess exacerbated by what we saw in the Millennium Drought, this period being the Millennium Drought. So what does the future hold? Let's just briefly talk about the method. Some people here may be interested in the sort of technical detail of what we've done here. So first of all, we used traditional, I guess, hydrological modeling approaches, stochastic modeling approaches that take account of the serial autocorrelation in annual rainfall and temperature, and the cross correlation, importantly, the relationship between precipitation and temperature in a given year. So when you have more precipitation, you have lower temperature, essentially. There's a few other statistical tricks, I guess you would say, in there to really get this model to look like what is realistic. So these are stochastic simulations that capture the basic statistics of monthly, annual, interannual rainfall and temperature. Technical detail if you're interested. We then say, okay, quite aside from what the climate models say is going to happen, let's just change the mean, change the mean state of the rainfall and the temperature and see what happens. So we generate changes in precipitation from -30 to +30 and changes in temperature from -1 degree to +3 degrees. We have a huge number of simulations that we run. We then have a calibrated rainfall runoff model for Melbourne's main storages, and this could be applied in other places. Calibrated model that achieves high evaluation statistics. So we're confident that it simulates a realistic behavior given rainfall, temperature, and a whole bunch of other parameters. This is the model there developed by Murray Peel and others, the PERM model. And we then run that through a simplified model of the Melbourne's main storages, where we have a model for the supply, we have some seasonality in the supply, we model the ins and outs of the system, evaporation, and so on. So there's basically a model for this entire process given a particular change in the mean state rainfall and temperature. From that, we then calculate the risk that this kind of bucket system, you can simplify it as, hits 10% or below. That's the risk that we're really worried about. If we hit 10%, we're in trouble. We may not have water coming out of the taps. So what is the risk of that happening? You can represent that risk, first of all, simply quite aside from the climate model simulations. So this doesn't include climate model simulations yet. We're just looking at if we simulate the rainfall and temperature in a realistic way, but we shift that rainfall and temperature by a given amount for different scenarios. So right down here, we're shifting by -10%. And here we're saying, what if the catchment's warm by an average of 1 degree from 61 to 90 levels? And we're representing in the color the risk, the water supply shortage risk. So this is essentially, what is the probability of being at 10% or below? Not a place you want to be. You do not want to be up in that red zone. This figure is before we had a desalination plant. This doesn't include desalination. If we come along and then say, well, what do the climate models say the precip and temperature will be at these different global warming levels? What does that look like? Where on the surface do these markers sit? And you can, first of all, you can see there's quite a lot of scatter. But if you look a bit closer, when we look at the natural current 1.5 and 2 degree world, there's basically a steady progression up towards this higher risk zone. And there's a lot of scatter, sure. Models project different, particularly different changes in rainfall in these different scenarios. But the key point is that we are moving into that zone, I guess. Now, on the left is the figure from the slide before, no desalination. If we add desalination into the mix, which is an approximation for the current system, an approximation, then we see that the risk declines and we have actually a bit of clear space for the current situation. You can then, and now this is for a given demand level. So essentially what we're saying is for a particular demand, there's a substantial reduction in when you add the desalination plant. I mean, you would want that to be the case, which we taxpayers of Victoria have spent a lot of money on that. And, you know, in some, I guess, in some ways, this may be somewhat of a justification of that spend. It's one way of obtaining water. We didn't look at that, whether that was sort of socially justifiable or anything like that. This is just a pure sort of look at the numbers. Now, what you might say is, but hang on a minute, Melbourne's growing. Melbourne is increasing its population. This analysis is all for a particular level of demand, water that we're all using. Melbourne's population is, I think, going to hit, perhaps someone at Delp may correct me, something like 8 million by 2050 or something in that rough realm. Don't know if anyone knows, but with population growth, the demand on this system is going to increase. So essentially that risk cliff is going to get closer than we want. So what you can do is to look at various demand scenarios. So on the left, we have, on the y-axis, we've got this risk, the median risk, and in each of the colors, these different worlds. So for a low demand scenario, this demand scenario is where we're using, on average, 70% as a demand of the annual average inflow into the reservoir. So essentially, we're using 70% of what's coming into the reservoirs. If we increase that to 75, 80, and continuing, what we actually see is, bigger differences between the 1.5 and 2 degree worlds as we go up into this high demand, higher global warming situation. And this is quite stark differences in risk. This is not somewhere that you want to be. You don't want to have a 10 or 20% risk of getting to 10%. That's an unacceptable risk to the supply of water to a major population like Melbourne. This again is without the desalination plant. When we add the real case, or an approximation for the real case, the risk certainly declines. And so this is good news to some degree. But the point is that as we increase our demand and get towards a high demand scenario, which is not unrealistic, and as we warm to a 2 degree world, we actually do see substantial increases in risk to the water supply of Melbourne, which was not known before this work. So with that, it's a brief talk, and I'm very happy and welcome to questions. So I will basically say the take-home message here is that global action on climate change will substantially reduce those external risks to the system. We are a wealthy country and we have the capacity to handle some of those risks, but those external risks will be there and they will cost. And so we can justify certainly action on global climate change, reducing emissions on this basis as part of the justification. So with that, I guess I'll just say thank you to people who have assisted with the work, and also probably just leave you with a few images just to recall what's actually going on right now in the country and how all this fits into that context. So thanks very much, and I'm very happy to take questions.
Thank you to Ben, very interesting. I can tell my dad was a former engineer at Melbourne Water. He used to crap on about that desalination plant forever. I never listened. He never made it as interesting as you did. Maybe you should have used PowerPoint. But so have you got any questions for Ben? Very fascinating. And I'll ask you to use the microphone just for the recording. I do apologise.
It's a question about timing. So you've got water corporation boards who are have to manage price and intergenerational risks. So if those boards were trying to ensure a security of supply for Melbourne, what's the timing for augmentation?
That is a devilish question, but a good one. Yeah, so I guess that comes down, ultimately in our society, that comes down to a political decision by a decision maker. And as scientists and engineers, I feel it's our role to present the facts, or the facts to the best of our ability, to present the risks, and to present the risks under various different options. And then really, it is someone's decision at the end of the day. So it really isn't up to you or me to say, this is when you should. And we may form a justification around a certain sort of framework for decision making. And this is one framework for this, or at least feeding into decision making, called scenario neutral approach, where we just sort of have that hands-off approach. We just say, we don't know precisely how things are going to change. Let's see what happens under a really wide range of scenarios. And then let's have a look at what the climate models or other models say will happen. So that scenario neutral approach can feed into that. But I guess my answer to your question is, ultimately, it is a decision for a decision maker. And I guess that's why we elect them. And, let's just hope they do their job.
Ben, under a growth scenario for Melbourne, to keep some level of acceptable risk in a 2 degree world, what am I allowed to use per day to at 70% of inflow?
By the way,
it's
that
hard
was
to put a
Mike
number on
Sandiford
that,
from
but
Earth Sciences.
because
just introduce yourself.
It depends so much on the other users in the system. It depends a lot on the variability. It depends on how rainfall will change. I could keep going and list about 60 things that it will affect. But
we showed that in the Millennium Drought.
Sure.
We can dramatically reduce it. But in terms of understanding what it means pragmatically, we have a certain inflow. We can augment that by production.
Yep.
It will be interesting just to give a figure. Are we safe if we halve our use, or is that not enough?
Well, I guess you can go back to figures here, and you could actually sort of back calculate what the average per capita use is. I've done this on the basis of like entire total demand, assuming that population growth leads to that demand, but of course, reducing the per capita use will affect that. But also the population growth itself is quite uncertain. So, I mean, I think there's just so many factors affecting that. My personal opinion would be, I don't think we should increase beyond per capita use of where we are now. I think we should continue to look for as many possible opportunities as we can to reduce per capita use. It's hard to put a number on it to say that that's a safe use because of all the other factors.
Thanks, Ben. So Andrew King from Earth Sciences. That was a really nice talk. I think what's really striking is just the big effect of desalination. And you made the point that we're a wealthy country, we can afford to do this. But you showed in your map other regions of the world with drying under 2 degrees of global warming, including lots of areas that are not as wealthy as Australia. So do you think this kind of highlights the, I guess, another inequality in climate change? And do you think there would be benefit to doing this kind of study in a country where augmenting water supply with desalination is a lot more, a lot less likely to happen?
Yeah, so thanks, Andrew, and a lot of Andrew's work has been feeding into this. So thank you for your contribution, Andrew. I really appreciate it. And you're right, and I agree. We are a wealthy country, and although we will and certainly are experiencing very severe impacts of climate change, and certainly aspects of bushfire and coral bleaching and drought, aspects of those really severe events are linked to climate change, and we have a capacity to handle some of it. But you're right, there's parts of the world that just can't afford multi-billion-dollar desals just built in a fraction of in a couple of years. So it may be interesting to look beyond. It comes a bit down to how confident we are at the climate models in some of those regions due to sometimes a lack of observations. It's a devilish problem, because do you really trust what the climate model is doing there if you can't actually evaluate the model at that point? But I think we can certainly do some work in that area. Interesting.
I have a suspicion that you're a bit of an optimist, in that my understanding is that climate crisis will increase the probability of forest fire in the catchments, and that in turn has effects on runoff. Would you take this into account?
That's an excellent question, and so it's actually the subject of a current review that is going on. I'm contributing to the climate aspect of that review, but there's other experts who work specifically on bushfire and the impact of the bushfires on runoff, essentially, from catchments. So you're right, and particularly ash forests are affected, and this is a known result from 1987. George Kazira, my PhD supervisor, actually worked specifically on this topic when he was at Melbourne Water. It wasn't called Melbourne Water back then, but yeah, I don't know if you have specific expertise in that area, but essentially what you get after a major bushfire is, for the first year or two, you actually get increased runoff and reduced water quality from all the erosion. And after that, for a very long period of time, you actually have reduced runoff, because the ash forests essentially sucking up, the younger trees are sucking up more water and evapotranspiring more of that water from the soil. And so you see this slow, I guess, initially a slow decline and then a slow recovery. And it's that exact question that we're looking at in this review. It's very uncertain exactly how bushfires will behave in the future, but just looking at observations and just looking at the impacts of recent droughts and really severe bushfires, you would have to say there's a reasonably good chance that we'll experience severe bushfires in our drinking water catchments at some point in the future. And it is a serious concern. So I agree with your point.
Any other questions you want to hear?
Oh yeah, thanks Ben for a great presentation. Andy Sheehan from Cardno.
I just, it's getting into a bit of the detail, but you spoke a little bit about some of the paleoclimate records, and I guess, yeah, just wondering what are the future opportunities, constraints in that space, and I suppose the challenges around acceptance of some of that, of adopting and using some of that data going forward, and how, obviously you spoke a little bit about some of the issues around length of data being an issue. Just wanted you to talk to that a little bit more.
Yeah, so there's a lot to talk about with that particular question. So first of all, on the development of paleoclimate records, North America and Europe is basically covered in excellent conifers that can be used for paleoclimate record sort of development. And that comes down to those trees being very well suited to what's called cross-dating. And what they do, they drill core, and they'll look at the width of the rings in those cores. They don't kill the tree, you just take a very small core. You measure those rings, and you do that for a particular area, like a region. And then you look at if we can cross-date the patterns in those widths of the tree rings, then we can actually say that a particular ring is in a certain year. So we can go, that there is 1726, and that there is 1654. You know, that's called cross-dating. That's very hard to do in Australia. We don't. The mainland of Australia is basically devoid of any conifer species that can do that. That's one of the main problems with paleoclimate reconstruction in Australia. Tasmania has got some really nice long conifers, and there's some iconic records of Huon pine, celery type pine, and a few other species, and they're beautiful record. Huon pine is one of the most magnificent, things that ever existed on Earth, if you ask me. But there's thousands of years. Ed Cook and his team and some of my colleagues have actually developed really, really long temperature-sensitive records. Another challenge is getting a sensitivity to hydroclimate. Rainfall changes. So a tree's growth is related to temperature and soil moisture availability and a whole range of other meteorological impacts. But narrowing that right down to like rainfall or soil moisture or runoff is a tricky part of the process. But we think that with some of these wood properties, particularly for high elevation where we're confident we can do cross-dating, we think that we may be able to get some long records. So I think, clearly climate change is a extremely serious and major thing to address. At the same time, we have to be cognizant of natural variability, and basically what we're getting into the future is a combination of both. So understanding that natural variability is really important, and so there's a very strong case for continuing to develop new records. I've only mentioned tree rings. We're also working on corals. There's a new project that's under review at the moment that's looking at developing new coral records from the Great Barrier Reef, looking at past bleaching events. There's speleothems, and there's a range of other proxies that we can look at. But we essentially need more work in this area, and we're pointing the way with this pilot project that maybe the wood properties are a real goer. So yeah, I hope I touched on a few of aspects of that, but it's a big topic. Yeah.
Any other questions? If there,
quick one on, you haven't mentioned much about reuse. Working with, there's 350 gigalitres that comes out of the Western Treatment Plant. There's about 400 gigalitres in an average year runoff on Melbourne roads, and that could be reused at much lower cost than desal. What are your comments on that?
I think I guess I'm looking at the big numbers, and I agree that there are so many different sources of water that we can use. I was part of a process for another region that looked at every possible measure, and it's highly specific to the region. It's highly specific on things like, can you store that runoff from the roads? Where do you put it? I mean, you need somewhere to store many gigalitres. Can you do sort of local, regional sort of storage? Can you, a big thing is industry using recycled water, I think is a big thing. Potential additional movement in that direction. And another option that I think should probably get some attention is actually recharge, using recycled water as a recharge of the groundwater, and then making use of that. So there's a whole range of options which we should consider into the future. And ultimately, I guess, which goes back to the initial question, these are decisions for our politicians, our decision makers. All we can do as scientists and engineers is present the full spectrum of options and assess the risk according to each of those options. So thanks for your question, and yeah, I agree. It's a good idea.
Okay, well, we thank Ben for a very interesting, very topical seminar today. I'm glad he's put this slide up because it does remind me of the final seminar we have for the year. It's on Monday, the 16th of December. It's being held by Claire Walter. She's looking at the link between air quality and climate change, and perhaps how we might use that to reframe the climate debate. So keep an eye out on our website, and if you're not on our mailing list, please do sign up, and you'll get all the details of our seminars. Big round of applause for Dr. Ben Henley.
Just a few ideas.
One question in the demand of the inflow that you hit there in the bottom axis for the 2 degree from 70 to 85%.
Yeah.
Is that
What's realistic?
Pegged to a certain historical year?
It's pegged to so you calibrate the stochastic model to the observed data, the full observed data. So it's basically related to that. Yeah, thanks for your question. So the Q part of it is basically the observations, the current observations to the point now, all the way to now. So it's the full period. But I take your point. You could easily adjust the instrumental. Like, yeah. But yeah, you're right.
Because I thought there was a little bit of redundancy there, because the risk comes of undersupply once, of course, your use is more than 100%, minus the evaporation from the dam, etc. If you use more than what flows in. So I thought, was that a historical metric, that 80% compared to historical inflow, and then you get the risk? Or maybe there I missed something.
We need to talk a bit more, because I still need to quite understand what exactly your point. But it's basically just saying all of the demand is 80% of all of the inflow.
Yeah.
So it's not really pegging it to you could peg it to historical. Okay. It may make, I think, slight differences in whether. Yeah.
Most of proxies in runoff too.
It's basically the best reconstructions that have been done in like Colorado, places in America where you've got soil moisture sensitive, but they're not.
It would be interesting to know if the proxy would develop into urbanization with forest densification and all the stuff which goes on, especially burning, not only but also for burning, management of the effect that had on insect population. But when they stopped that, those big trees died because of insect infestation. Well, so he was observing from 1860 to 1890. He was a geologist, then became a naturalist. A lot of work. Very interesting report. But those landscapes which changes, the fact that indigenous building was much more open forest, the forest just densified almost instantaneously because of the.
And you also had black and ice.
Well, yeah. So out on the plains you did, but up in the hills, something gets a filth in you. But it will be interesting to know if it's your policy that would look at the
the rainfall transmission, you would expect that. Well, I don't know.
Yeah,
So,
if you could find one, yeah. It's a yeah.
Hi, I'm Paula Hanaz. I'm from DELP, Manager of Climate Change Education. What's that called? Well, I know we think too about it. So, to that point, that's my job. To that end, I think some of the fireworks you're doing with DELP, right? Yeah.
They're one of the logos.
Yeah, no, I know. I was just wondering which, obviously,
We are in the smart century. Everything's smart now.
Everything's smart.
Yes, since the mankind never been. I know. It's all, from beginning, everything was done, no much talk. Now so much talk, nothing done. Smart money, nobody talk about money, smart money now. People are dead. But they don't think that people should work and bring the money, give it to people they can spend, business can go. And Mother Nature give us free heating and cooling. Look at this, now we summer. Hey, summer. Father Christmas come from North Pole, bring us winter here, once have a white Christmas. This is unbelievable. Okay, all the best, enjoy it, and happy
Thank you. Have a nice Christmas.
New Year and a nice Christmas too. Enjoy it.
Thanks so much.
I like the comedy show from America, Mr. Trumpet. Yeah, they got the birthday cards, Did you see? 2016. Okay.
Thanks a lot.
Nice. Have a nice Christmas.
You too. Yeah.
So, long story short,
Yes.
first and foremost, would you be available interested in coming to this presentation to excellent. Let's make that happen. Secondly, looking longer term, as you're really aware, under climate change being sectors that have obligations to develop their own climate adaptation plans. Water sector is actually, believe it or not, sectors which are climate partnership. Actually, I've sort of got some questions also about how these projections affect.
Please remind me of your name again.
Paula Hanaz.
Okay, thanks, Paula.
Follow up with an email.
Can you, I was going to say.
But basically,
Yeah,
I'm
so
sort of
agriculture as well.
agriculture as well. The water sector, the Melbourne Water Corporation of Victoria, so now halfway through the pilot education action plan with a series of community projects focusing around establishing an evidence base for stuff. As we're moving towards the next education action plan, which was put over the pilot by the 2021, we're thinking a lot more about better scenario-based adaptive planning, interdependency with other sectors, collaboration, that kind of stuff. To that end, the very first piece of work will be commissioning early next year. We wanted to do a so basically we're thinking that, but with specifically the involvement of and seeing what those projects might need to. So I assume we've got somewhere to be quite
Really involved. Yeah.
and
I think it could be done if we have decent instrumental records that can calibrate that.
Yep.
Those targets calibrate that.
Yep.
But it does provide a framework to at least.
Yeah, absolutely.
Captains will respond.
Yeah.
Precipitation is working. Excellent work. Massive bushfire, rainfall-runoff.
And then sort of all mitigated by stuff that's already happening on the ground, right? We're going to like all of the recycled water stuff that is beginning to happen.
That can sort of reduce that demand point, I guess.
Yeah, exactly.
If you just look at,
There is
a demand in that. I mean, each of my
that's right.
It's quite a different demand level, so you've got to kind of make one way or another. You have to sort of specify something in order to get numbers. But you can at least look at a big range of options.
Well, I'm sort of interested in having this sort of a methodology with some from water corporations to be able to tell you, well, what's the but I think it's fascinating. But my background's social science.
Well, it is. I mean, the gains that you get. Using the demand.
Well, I think you answered the question earlier about targets.
I mean, I was used in that.
Exactly. And it's not necessarily meaningful metric as well, because like if 9% of that is like
there's a whole lot of complicated factors.
So it'd be so we're looking towards finishing that work next year. At the moment, it's not anything. Then I just Victoria. Weird. So his team kind of worked on the science side of things. We work more on the governance side. So we're part of a resilience team, which also looks at emergency management, which is another big aspect. And general, which is it's nice. It's really complex. It's related. So one of our this is very much the risks, operational risks, not just in terms of supply, but in terms of say capacity. When you've got bushfire season and you've got roles, and they spend now 4 or 5 months rather than 2 months activating those roles, you literally have capacity to be doing going on customers. These are good for business. Exactly. Which is a different we've been doing this work on very interesting findings about is that even know. Just random things about
the cost of human system.
But I mean, so some of the case studies have been this is actually done most before in the role. But it's an asset-based, specific assets that are more broad to operations and things like things. But things like when you're collecting data that's say got monthly data, you can't